colleagues might use, double quotes plus I, or integer.toString, integer.value_of, string value_of, integer.getInt integer. So we've got a poll live on slido.com. If you go to room 1, GeeCON 2019, you can vote, and we can see how voting works, right? Maybe we can show some other people how it works. So here we go. This is the poll. And once you've voted, then we're going to move on. So pop over there. I'll give you a few seconds. And it looks like, so far, the double quotes is not doing too well. That's obviously the lazy way. Integer.value_of is the clear winner at the moment, so this is fun. And all right, this is very good. Okay, there you go. Integer.value_of, integer.toString. Interesting. I know that some of these methods don't actually exist. So, all right, fantastic. Let's look at the next poll. So the next poll is the following. We've got 4 methods, 4 different ways of appending strings to each other. So here I want to build up some web page, and I've got some data, and I'm appending it into this web page. And in the first way, it's again the lazy way, just using plus. The second way, I'm creating a string builder, doing it a bit more, the right way. The third way, I'm first working out how big the arrays needs to be inside string builder to stop myself from having to create unnecessary string builder or unnecessary char arrays or byte arrays inside the string builder. So I don't have unnecessary arrays being constructed. And then the fourth one is another one where I've got format. And with format, of course, we've got regular expressions, so 1 million objects later, right? So let's do the second poll and see how that works. Well, let's see what do you think is fastest? All right, so far the append basic and append string builder size are sort of leading. Append format is lagging behind a bit in the polls. Not so good, okay, right. Good, very nice, fantastic. All right, well, you can continue voting if you want. I'm going to continue with the talk. So we're going to start with Java 1.0, when the dinosaurs roamed the earth. And in Java 1.0, when they created string, they had inside 3 fields, private char value array. Now, this was, these guys were C programmers, so, they put the array at the back, and private int offset and private int count. And they used sampling when the string was long to generate the hash code. And the logic was, it doesn't really matter if the hash code is not unique because, well, it's a hash code. It's allowed to not be unique. It doesn't have to be unique. So when the char array was bigger than 16, they simply took 8 samples. I'll show you the code in a moment. Equals didn't check whether object equals this, and in turn used a static hash table. So there was actually a memory leak in Java 1.0. But, it's okay, it sort of worked. And they had a string buffer, which is a bit like a vector of type char, a vector of primitive char, which basically means a thread-safe collection of characters that you could change. And toString shared the underlying char array. That was quite fun. So basically, you said toString, and the string buffer pointed to the same char array. And if you then afterwards changed the string buffer, then the string buffer internally would make a new copy of the char array and change that. And the string would keep the old char array. This was in order to prevent or avoid having to create unnecessary char arrays. This is what the code looked like in String 1.0, the hash code. And if you look at this, if length is less than 16, they look at every character, and they have some weird multiplication times 37. A prime number has got to be better than not prime number, right? Otherwise, they sample some of the characters. And they basically take the length divided by 8 And so they look at 8 characters in the entitled string. So you could have a string of 10,000 characters, and they would only look at 8 of those characters. You can imagine that you could have a lot of clashes when you had hash codes with the same value. Oh, by the way, I'm not Dmitry. I'm only Heinz. I apologize. Unfortunately, Dmitry couldn't be with us due to something stopped him from coming. So you're going to have to listen only to me. So now is a good time to get out if you want to. So Dmitry is a really, really clever guy. He's been doing a lot of JMH tests. And so we started talking about this talk, and he's done quite a large chunk of this talk, but as I said, unfortunately, he couldn't make it. So I'll try and fill in as much as I can. We organize JCrete. I write the Java Specialist newsletter, and I've got a surprise for you if you go there. I won't tell you what it is, but it goes away at 2 o'clock, the surprise. Right? There'll be a smaller surprise. If you're watching the recording, have a look at it as well, but there'll be a smaller surprise for the recorders than for you guys sitting here. All right, so Java 1.1, the field stayed the same as Java 1.0. The hash code was still sampling like in 1.0. They moved in turn to native code, which wasn't necessarily faster than using a hash table, but of course they could manage the memory leak a bit better than in the past. They had some other weird side effects, like if you had German and you did 2 uppercase on the SZ, you would actually get 2 big S's, because at that time, we didn't have the uppercase Unicode for SZ. There is one now, but at the time, there wasn't such a thing. 1.2 feels still the same. The hash code changed. And in the past, the hash code used to be, as I said, sampling. So you only in the worst case scenario, it was 15 lookups. As long as it was bigger than 16, it would only look at 8 of these characters. And you can imagine what happened. First of all, a whole bunch of people were really upset that the hash code changed, because they had written tests that assumed hash code would always be the same. But hash code changed, so the tests broke. And in fact, that was the last time that Sun/Oracle dared to change the hash code of string. They didn't want to make people unhappy. But there's some other side effect which I'll talk about in a second about this. They also introduced a comparable interface. Now, in Java 1.1 and 1.1, the hash code calculation of a string was constant in time. You could never get a worse case than order 1. In Java 1.2, it changed to linear time, the calculation, because we now looked at every character, not only 8 characters within the hash within the string. So if you have 1 million characters, you have to look at 1 million values and add them up. At the time of Java 2, there was a great book written called Java 2 Performance and Idiot Guide. Idiom Guide. Idiom Guide, right. Now, it was a great book for the time. And one of the things with performance books and performance articles is that as soon as you write them, they're out of date, because everything changes around you, and what was true in those days is no longer true today. At the time, they made a very strong persuasion to say that you should always wrap a string with another object and then cache the hash code. And their reasoning was that they wanted to avoid having multiple calls to hash code on a string and then having to have linear performance every time. And there was a large chunk of that book. Now, if you look at this, right, here's a class key, and the hash code is slower than your hash code. It takes 100 milliseconds to call hash code. And so if you call put 30 times, it's going to take you 3 seconds, right? Because when you call put, you call hash code once, the hash map calls hash code once, and then it's put into the hash map. But inside the hash map, the hash code has actually been cached as well. So the key inside the map knows what the hash code is internally. So it doesn't have to call the hash code a second time. It doesn't call it every time that you look up. And similarly, when you call get 30 times, you are most likely going to recreate those keys, because if you don't need to recreate them, well, then you might as well not use a hash map, just store them directly. And so it's going to cost, again, 3 seconds to call get 30 times. So the idea of caching hash codes wasn't that useful, but they decided to do it anyway in Java 3. So that's why I'm saying that the book on Java 2, Performance and Idiom Guide, became sort of out of date when Java 3 came around, because the most important factor was actually put into Java directly. So now you've got a field hash inside the string. Now, something which is interesting is the size of pointers. At the time, a lot of us were working with 32-bit Java. This is Java 3. And in 32-bit Java, a Java object, at the minimum, costs 8 bytes, right? A pointer is 4 bytes. So the cost before in Java 2, let's go back to what we had in Java 2, the fields were basically the same as right here at the beginning. It was the object, which was 8 bytes, a pointer to the array, the char array, which is 4 bytes, another int, which is another 4 bytes, and a count, which is another 4 bytes. And the reason there's an offset and a length is for substring, that they could share the same underlying char array for multiple strings. So if you say 8 plus 4 plus 4 plus 4, what does it equal to? 24, right? Correct? Is that right? 24? Well, it's actually 20, but it gets rounded up to the nearest 8 bytes, multiple of 8. So what you had is you had 4 bytes spare inside that class in 32-bit Java. And so what they, by adding the hash code in there, they could actually sneak it in without it costing anything on that particular architecture. That was quite neat. So it was like a free thing to have. And there's the hash code, and if hash equals 0, then we work out the actual hash code here. All right, so before I came here, I went to the telephone directory of Krakow, and I got some names out for you. You know these guys? Okay, no, it's not a telephone directory. What do these strings have in common? The hash code, right? What do you think the hash code is? It's 0. Exactly, well done. So all these strings happen to have a hash code of 0. I wrote a brute force algorithm to find them. You can actually generate a string of whatever hash code you want by going in reverse, the hash code algorithm in reverse. But I want to find a whole bunch of strings of length 7, which are alpha, just characters, upper and lowercase characters. And then I wanted to have all these strings with hash code 0. And you can generate, quite a few of these strings with hash code of 0. Now, what they've got in common is that the hash code is 0. Now, the problem with that is, if I've got 2 strings like that and I append them together, the hash code is 0 still. Because once you get to 0, you multiply by 31, it's again 0. So any combination of these strings is also 0. And so if you've got just a few of these strings, you can generate an endless stream of strings with hash code equals 0. And this is an issue, right? So let's have a look at what can happen. You can very easily attack a server by sending it lots and lots of hash code, lots of strings which have a hash code of 0. And as I said, it would be more difficult if it was a hash code of 42, because to generate all these strings, it takes a long time. But if I want to have lots of strings with the same hash code of 0, well, I can just combine these strings and get lots and lots of these. And then your put and get becomes linear. Let's try it out. So here's my program StringDos. And what StringDos does is it's got just a few of these 0 hash codes, and then it just combines them, and it puts them to a hash map, and then afterwards it goes through several times, test lookup, it goes through a million times, and calls get with each of the strings on the hash map to see how quickly it does it. And in Java 6, and I've compiled it with Java 6. Let me go to the... So Java 6, Java C, Java Specialists, Playground, hasher, string.dos.java. So compiled with Java 6, and then we say Java Specialists, Playground, hasher, string.dos. And you can see that as we double the size, double the number of elements, it becomes about twice as slow. So you can see that it's linear in cost because you're ending up with a longer and longer list, linked list of nodes inside there. So we double the size to 512, and it jumps from 900 milliseconds to 1.8 seconds. So this, of course, is not fantastic. All right, we'll get back to this in a moment. Java 1.4 had the same fields as 1.3, but they also had another interface called char sequence, which was implemented by String and StringBuilder, String Buffer at the time. So now you could write your code to accept a char sequence, so then you could either pass in a string buffer or a string. That was quite convenient. And they had regular expressions, like matches, split, etc. Now, if you look at this string, if you add strings together, like here I've got hello, and I say hello plus arg0. String plus a string, constant string plus a string added at runtime. In Java 1.0 up to 1.4, they wrote the code so that it would generate a string buffer. So they would make a new string buffer, .append hello, .append args, .toString. The initial string buffer would create 16 characters, and then whenever you add to that, it would possibly extend that to have space for your additional chars. So that's what's generated. And in Java 5, the fields stayed the same as 1.3, but they marked them as final, except for hash, of course. And if you think about it, we all know that strings are immutable, right? Well, actually, they're not. They're not actually immutable, technically not immutable, because when you construct a string, the hash code inside will change. There is a data race within string. But it is a benign data race, because if two threads call hash code at the same time, they might both work out the hash code, and they might both overwrite each other's results, but because it's a 4-byte int value, it doesn't matter. We'll actually overwrite it in a safe way. So it's got a benign data race. But we can treat it as if it was immutable. All right, so we've got Java 5. They also had code points, 32-bit characters, and they added a class called StringBuilder. Basically, they said we don't want to pay for the cost of synchronization within string buffer if we don't need it, because most of the time when you use string buffer, you actually don't, you're going to throw it away within the method. It's method confined, or called stack confined. As soon as you exit the method, we throw away that string buffer. So there's no reason to make it, to have it something that's thread safe. And so they added a string builder. Now the funny thing about that is that they actually added a class and disrupted the whole architecture for something which they didn't need to do. And in Java 6, they actually added technology to automatically elide locks, to get rid of locks you don't need and throw them away. But at the time, they didn't have that technology. So we've got string builder and string buffer. So wherever we had plus inside a method, they replaced with a string builder rather than string buffer. And this meant that you needed to recompile your Java code in order to make it faster with the plus. Otherwise, if you had handcrafted string buffer code, then that would typically normally be slower than the normal plus. Right. Java 6, not much change inside the string class, but they did have a feature called compressed strings. This only worked if you had only ASCII characters, US ASCII, so 7-bit characters. Then it worked. And the byte array, so the compressed strings would either use a byte array or a char array. So this was quite funky because if you do a reflection, for example, you don't know what you're going to get. It might be byte array, might be char array. Also, if you're doing profiling, some of the strings might show up as byte arrays, others might show up as char arrays. You didn't actually know what would show up at the time. Another thing which was really big was when they added optimized string concat. And this meant that in some cases they could share the char array between your strings and your string builder or string buffer. So this trick I mentioned at the beginning, where they had the same char array between string and string buffer and string builder, that actually still happens. Right? You can, if you look at the memory consumption, you can deduce that that actually happens in the background. Now that quiz I put up at the beginning, append basic, append string builder with a size, there was a trick which I didn't tell you. And the trick was that I added only strings together. And if you're adding only strings together, all three are exactly the same. The first three are exactly the same. Append basic, append string builder size are exactly equivalent. At the moment, the format is still a lot slower, but that is changing. There's already a preview build available that you can use for string format to, I think it's Project Amber, to be as fast as just normal plus. So use whatever is easiest to read. Java 7 came along, and they recognized the problem with strings that have a hash code of 0, always the same hash code. And so what they did was they added an alternative hashing into string. And the hash map would check, is the key a string? And if it's a string, then it can use the alternative hashing mechanism. So that's really cool, transit hash 32. So if you run the code that I showed you earlier on, oh, it's still running. I thought I killed it. It didn't do it. If you run with Java 7, the code, same code, you'll notice that now it's still exactly the same. So I knew about this whole trick that they had, but and I thought all my servers were now safe, but I never tried it out, and I never tried running it, except when I was preparing for this talk last year, and then I realized it only works if you enable it explicitly. You need to do this. You need to say -d JDK map alt hashing threshold equals 512 or whatever threshold you want to use, and then it uses that hash 32. So you can see that as the hash map grows, it's still as slow, but then once it reaches a certain size, it uses a different hashing mechanism for this, and now it gets much faster. Because of course it's no longer linear lookup, it's now getting closer to constant time lookup. So that's our string DOS. So you could use that, but you had to enable it explicitly. And of course, if you enabled it explicitly, it was for all the strings. So if you had any, I don't know, like tests that assumed that the hash map returned elements in a certain order incorrectly, right? If that was your assumption, then your test would break. And they, again, actually solved that particular problem for a general case in Java 8. I'll talk about Java 8 in a moment. They also had another constructor added with a char array and a Boolean. It was package access, so you shouldn't be able to call it directly from the outside. But there was a class called shared secrets, right? And calling something shared secrets is as bad as calling something unsafe. When you call it names like that, Java programmers are going to say, how do I use that, right? Where can I get that? How can I use the shared secrets? So with shared secrets, you can actually create a string with an existing char array. And it would share the char array. So when you change a char array, it changes a string. So this, again, breaks this whole notion of immutability of strings. Another thing that they did in Java 7 is you notice that they changed, instead of having offset and length, they only have a pointer to the value, to the char array. And what they did there is they changed it so that whenever you made substrings, it made a new copy of the char array that you want, of the sub-char array. This, unfortunately, tended to construct a lot more char arrays and sometimes waste a lot of memory. The thinking was this. In the past, somebody might get a big string, say, for example, 1 million characters, but they only need the first 20 characters. So they make a substring in order to save memory and put the substring into a map somewhere on the first 20 characters. But in the past, what would actually be used would be 1 million characters, because it would be pointed to the existing char array with offset 0 and length 20. And too many people made this mistake of assuming that when they make a substring, it's a new string with a smaller char array. In order to solve that problem, they changed string so that it would make a new char array to avoid this particular memory consumption. If you want to have a subbable string, I've written one. You can have a look at my newsletter 230 that shows you how to do that. Java 8 came along. They threw out the hash 32 because they solved the problem in a general way. And if you run the same code with Java 8 that it did before, we don't need any special settings. You notice that as we double the size, it becomes a bit slower, but not excessively slower like before. And what happens is at the moment that your bucket has more than a certain number, I don't know if it's 8 or 13 or some number like that, elements, it constructs a binary tree. So your performance degrades to order log n in terms of lookup. I mean, the performance is really much, much better than it was before. So your worst case scenario is order log n. Now, there's something you need to be aware of. If you use your own keys in a hash map, make sure that your key is also comparable, because that allows the hash map to build up a nice binary tree for you. If you don't make it comparable, then you still can have order n performance when you look up. Something else, they had a bunch of static methods for joining strings and deduplication of char arrays. I'll mention that in a moment. So since Java 8 108.20, they've got the ability with the G1 collector, but unfortunately only with the G1 collector, to deduplicate strings. Now, I've mentioned intern before. What intern does is it gives you a pointer to the same string inside a shared cache as if you had a constant string somewhere. So that's what that gives you. So intern is a bit different. With deduplication, what they do is, if I've got two strings, which I've, for example, read from a database, read from a file, and those strings happen to have the same contents, then what they do is they share the underlying char array between the two strings. So that's quite neat. And this happens automatically. It gets done before the string ends up in the old generation. So normally there's some threshold after which it will try and deduplicate the string. It can decrease performance of your system because, of course, whenever you have a string that needs to be garbage collected, it needs to check, has a string existed already? And if it does, let me get it from the shared char array, get a shared char array. But it can also save a lot of memory. So have a look at that. And here I've got a char array which I've constructed, some catch-up make there. And I make two strings, which will have their own char array internally. And before GC, you can see that they've got different char arrays. The identity hash code is different. That's the thing on the right-hand side. Identity hash code is a random number that gets generated. And after I've called system GC, and I've waited for a little bit because once we want to deduplicate, it still takes a bit of time, so you can't immediately check, but if you sleep for a bit, after the GC, then you notice that the char array is actually the same now. And when I was sitting in the previous talk, I was playing around with this a bit. If you take this deduplication demo over here, if I run this in Java, this is Java 11, you'll notice a couple of changes. First of all, oh, no, I don't want to do that. All right, maybe it did actually run. Make sure it ran. Right. You notice a couple of changes in Java 9. First of all, it warns me about accessing private data from a string. You notice that before, it's a byte array, not a char array. I'll talk about that also in a second. And it didn't actually do it because I didn't turn it on explicitly. So let me just do that, run that again. And we need to do that with a setting. I need to change the view, otherwise I can't see. So let's edit that. And -XX plus use string deduplication. And now you can see that after GC, the byte array is the same. But what I wanted to show you is if you have a constant string, like name equals Heinz over here, so constant string, name equals Heinz, then these two strings will probably share that one's char array. So if we run that, you'll see these two byte arrays, which are different to the constant string, but afterwards they've got the constant string's byte array inside. And of course, the actual strings are all different. If you say equals equals, they would be different strings. Just the contents are the same. All right. Now, deduplication, intern, roll your own. Which one's the best? Deduplication only works with G1. And you have to turn it on explicitly. Now, if you look at a string, hello world, in Java 8, if you take Java 8, for example, with 64-bit compressed oops, that's what we use most of the time, your actual string object will take 12 bytes for the object header, plus 4 bytes for the value, the pointer to the value, plus 4 bytes for the hash, which is equal to 20 bytes, but it gets rounded up to 24 bytes. The char array is 12 bytes plus 2 times 12 characters, it's 24, plus 4 equals 40 bytes exactly. So it adds up to 64 bytes. When I use deduplication, the char array can be shared, so that will save 40 bytes for the string. If I use intern instead, then I can have both strings point to the same string inside the constant pool, but it's actually quite a high cost. And in Java 6, your intern table was limited to about 1,000 entries. And they changed that in Java 7. Now, since Java 7, it's about 60,000 entries inside the constant, inside the intern table. But even until Java 10, the intern table did not grow in size. So if you had 1 million entries inside the intern table, let's say had lots and lots of unique strings, then your intern table wouldn't grow, and you'd have lots and lots of clashes. So in Java 9, in Java 11, the intern table grows. So it doubles every time you run out of space, or every time you have a certain fill factor. Now, there's a really useful tool called JCommand in Java 9 from Java, that since Java 9 shows you details about what's actually inside your string table. So I've got IntelliJ running at the moment on here. And if I say JPS, this ID over here, 14524, I believe is IntelliJ. So let's try that out. JStack, that number, I think this is IntelliJ. Let's assume it is. So if I say JCommand, this number, and help, it will show me what is supported. One of the really nice features here is the string table. So I can do this and say vm.string table, and this now shows me that I've got 131,000 buckets, 136,000 entries, and the average bucket size is 1.045. That's pretty good. Now, if you'd looked at this in Java with Java 10 or before that, this is running Java 11 or 12, I'm not sure exactly which one, but before that it would have been 60,000. That's it, no change. The maximum bucket size is 8 over here. So things have improved with the string table, but it's still a native method call, and it is actually still fairly slow. And if you want to do your own, or if you've got lots of strings you need to that are often duplicated, it often is better to use just your own concurrent hash map. The only problem is that the concurrent hash map will never delete entries from the map. So maybe occasionally you want to just clear that map, like once a day, clear the map or something like that. But it's a lot faster to call putIfAbsent with string comma string than to use intern. So keep that in mind. What happened in Java 9? Well, Java 9, we ended up with a byte array for the value and another field called coder that lets you decide what type of encoding you want to use for this value. So since we're in Poland, I wrote a little demo for Poland, specifically for Poland. And it looks like this. So I've got a string builder, and I say append hello, right? Hello there. I then convert it to a string, and I print out the length of the string. I then append hello again, and I print out the length of the second. Oh, yeah, I had a mistake there. Ha ha ha. Copy and paste mistake. I then print out the length of the second string. All right. So what do you think it's going to output? Anybody? Just shout it out, and I'll repeat. How long do you think that the okay, the first one we probably think is going to be 5, right? How long do you think that the Polish string will be? 5? 10? Okay, who says 5? One person. No, a few people are there as well. Who says 10? All right, you are both wrong. It crashes. Well, it actually crashes because it says UTF-16 size is 2 million, should be less than 1 million, right? But it actually, the S1 length worked, right? The S1 length worked. Because when I had the S1 length, it was only Latin characters. But the moment that I try and put a non-Latin character in there, you know, those not UTF, not what's isolated 591 or whatever it is, these L's over here, they cause a problem. Then what it does is it changes the coder, and it needs to double the size of the underlying byte array. And because I sneakily made the size of the byte array 2 million up here, it ran out of memory. That was a sneaky question. Yes, but I got you right. I got you nicely there. All right. Another thing which is really important, is that, remember Java 4 to 5, we had to recompile our code? Because they changed the way that they implemented the plus. It went from string buffer to string builder. Well, they also wanted to change that in Java 9, the way that they create the strings. But they didn't want us to, in future, have to recompile our code and recompile our code with every Java version in order to get the improvements of the plus. So we now have a new mechanism since Java 9 where they replace the plus with invoke dynamic. And they delegate to a class called string concat factory that appends the strings together. Now, all of these demos, benchmarks, are all on my GitHub, String Performance. You can try them out yourself. And remember the second poll I gave you? It was a trick question. The trick question was that I was adding strings together. Well, here I'm actually adding mixed parameters together. So some strings, some ints. And when you just add strings together, there's no difference of what you want to do. But there is a difference when you've got mixed parameters. And you can see here that in Java, from Java 1 to 6 up to Java 8, The difference, the fastest was the string buffer sized. So if you pre-sized the string buffer, or string builder, you pre-sized it, then it used the least bytes, and it also was the fastest. Format was really slow, as you can see here, really, really slow. But since Java 9, and Java 11 includes Java 9, it's just the latest ones. Since Java 9, the fastest is actually the plus. Look, the plus is actually better and creates a lot less objects, a lot less bytes than the other ones, all the other ones. So what you really want to do is use plus when you're adding strings together. Don't use StringBuilder to add strings together. There's one little exclusion to that we'll talk about in a bit. But in the future, we'll be able to use format, and format will have the same performance as the normal plus. So if you've got format, you don't need to change your code, you need to change your Java version one of these days. Now, there are a whole bunch of algorithms for concatenating strings together. The one that's used is inline sized exact. So that happens to also be the fastest, so there's no reason to actually use the other ones. It was just for debugging purposes. And here you can see the performance differences. The fastest, as I said, is the first one. They also changed the type to be byte array instead of char array. This saves space if your characters fit into a byte, so Latin 1. The moment you've got one non-Latin character, like the Polish L, then it changes it to UTF-16. So you then have 2 bytes per character. You can turn it off if you want to. But as we saw also, the maximum string length is now half of what it was before. With and with off and on, there is a difference. And the difference is mainly the number of bytes that are allocated. So you can see in the plus, for example, the top one, if I've got compact strings on, this is with Latin strings, it's 152 bytes per operation, whereas with compact strings off, it's 264 bytes per operation. So there's a difference in how many bytes are being allocated. Now, something else which we need to keep in mind with string is that a lot of the string infrastructure is supported by intrinsics. And there are quite a few in Java 8. In other words, when you call in compare to equals, the compare to and equals methods that you see inside the string class are not actually what is called. What is called is some handcrafted C code. Java 11, there are far more. And where this comes to play is with string equals. You see, string equals has either Latin 1 comparisons or UTF-16 equals. So delegate to that. And in equals, you see at the top there is an @hotspot intrinsic candidate. This will give you a clue that this could be replaced with intrinsics. Now, if you take this code and you run this code as it is against the Java equals, you'll notice that the handcrafted one is a lot slower. But the reason is vectorization. So we have, if you write equals method like this, we say arrays.mismatch, and you use vectorization to do the comparisons, you actually end up with a faster comparison. So string equals versus mismatch equals versus hand-rolled, if the length is small, they're equivalent. But as the length grows, they start to deviate. And the reason is the way that do the vector comparison. So if length is 256 and the strings are equal, then it's going to be a lot faster comparing it with string equals than if you wrote the code yourself by hand. Deduplication is not taken into account, so they don't check, is it the same byte array? They really should, but for some reason they don't check that. So lessons from today, we have another 5 minutes for questions as well. Use plus instead of dot append. Don't forget to get this URL because it's going away at 2 o'clock, which is very soon. Also, if you're inside a loop, you still want to use StringBuilder.append. That's not going to go away. You try not to use intern. Use StringBuilder duplication or your own cache instead. Hashing can be very expensive. And also, since Java 9, we've got a byte array instead of char array. So it might use a lot less memory, but maybe not if you're in Poland. Maybe here you'll actually use the same. Right, so let's have a look quickly at the questions. If you'd like to ask in the traditional way, you're welcome to do that too. How does this work? How do I see questions? Would there be questions if I... Oh. There are no questions. If you have questions, please type them in here or put up your hand. We've got a few minutes. Or you could rush out and get some lunch. That's not a bad idea. So thank you very much for listening. I really appreciate it.